So tonight we're going to talk about what we call displaying and summarizing bivariate data. And what that really is we're going to display and summarize data through linear regression. And what happens now is everything we studied up until this point is what we call univariate data, which means that we've looked at one particular variable and gathered measures on that one variable, right? And so now what I'm going to do is I'm going to look at more than one variable. I'm just going to look at two variables, which is why we call it bivariate data. I'm going to look at two variables, and they're two quantitative variables. So they're going to produce numbers. And what I want to see is there a trend or some kind of pattern or association that can be developed between those two variables. So this only works, though, with quantitative data. Bivariate means two, right? And in linear regression, we deal with two variables, and those two variables are called, you normally see X and Y when you think about your variables. We're going to give them special names, but they are what you already know. And so the first thing you already know is that you have a variable called the independent variable, and that's your X variable generally. In regression, we call it the explanatory variable because it's going to explain, it explains what's happening or the different changes in our dependent variable or the Y variable. Our dependent variable is called the response. So as I change the independent variable X, how is Y responding? All right, as I change the independent variable X, how is Y responding? And generally what we say is as your X variable starts to increase, there's a relationship that's going to form with Y. And so Y can do one of three things as X increases. Y can first, as X increase, Y can increase with X. Or as X increases, Y can decrease with X. We call that an inverse relationship. Or the third thing is that as X increases, we don't really know what's going to happen to Y. We can't really tell anything what happens to Y because Y can go up or down. We don't know. All right. And so just like when we did our univariate data, we tried to graph the data first. We want to graph the data, look at it, because what you do generally is you want to display your data to see what's happening. And in this particular thing, we're going to use a scatter plot to do that. We're going to graph our data with a scatter plot. We're going to graph our data with a scatter plot. All right. Yes, I will do that. Post all my stuff. I will do that. So most of them are already posted, by the way. They should be in the actual week folders. I need to post the completed ones that I get done with, but yeah. So we're going to use that to summarize the data. We use a scatter plot. And on a scatter plot, all a scatter plot does is it takes the, a scatter plot takes the X variable or the explanatory and puts it on the horizontal axis, and it takes the response and puts it here. And our goal is to show the trend or relationship between the two. And again, this only works for quantitative variables. We only use regression for quantitative variables. Quantitative variables mean that they have to be what again? What does quantitative mean?
Your numbers.
It has to be a number. So we only deal with numbers here, all right? Now we're going to plot those values to look at them, okay? So let's take this from an example standpoint, and we're going to go with this through Excel. And anytime you do regression, you're going to do a lot of it in Excel. All right. So here's an example. It says, and this is actual data from one of my high school classes, by the way. So the following data was gathered in one of my high school classes of a student's attendance and their scores on the start date on the STAR state testing exam. So what you have is you have students that have attended their attendance rates, right? These are attendance rates. And on the STAR state testing exam, I think the highest score you can, I know the highest score is a 60, by the way. The highest thing you can score is a 60. So when I look at this, then a student who attended 95% of their classes made a 45, while a student who only attended 76% of their classes made a 35. are we surprised by that in general? Do you think attendance and your score are related together in some kind of way?
No.
Let's think about that. Do you think the more, so if the more you come to class right now, do you think the more you come to class, the better your score, or the more you come to class, the worse your score? Or it really doesn't matter?
Better.
It's all in how you retain the information.
It could be, but chances are most people who sit in the class are going to pick up more information than those who aren't in the class. We'll say it like that.
Yes.
That's what we're going to say. So typically speaking, the more you attend, the better your class, the better your scores tend to be. That's a typical thing. And just looking at the data right now, you might be able to actually glance and see that. But an easier way to see it is to actually put it in a scatter plot. So that's what I'm going to do first, all right? I'm going to put this into a scatter plot. So if you look at the Excel spreadsheet that I put up there, let's go ahead and look at that real quick. So here go those values in Excel. Here goes those values in Excel. And what I'm interested in now is to actually show these values into a graph. So I'm gonna use a scatter plot. So what I'm gonna do is I'm gonna highlight these variables here. And up here, I'll go to insert. And generally speaking, when you go to insert, if you go to recommended charts, Excel will give you a chart that you can use. Notice here goes the recommended chart they're giving you. They're giving you the scatter plot. Excel knows that you have two variables and they want to plot, you want to plot them like that. And again, when you plot these variables, they have to be quantitative. First off, does everybody understand that?
Yeah. Yes.
Secondly, when you're plotting them as pairs. So you can't like rearrange the order of the pairs, by the way. You're gonna plot 95 with 45. You're gonna plot 89 with 42. You don't want to sort this data. You want to keep this data like it is, all right? So when we look at this, let's click insert the scatter plot. Very simple thing to do. We get this graph here. And what I'm actually interested in now is the trend of the data, the actual trend of the data, right? I want to look at this trend. What do you notice about it? Well, first off, let's talk about let's talk about the actual data itself. Let's talk about the plot itself. This x-axis represents the explanatory variable. In this case, the x-axis is the attendance, your attendance rate, right? And then the y-axis represents the raw score, the raw score here, right? What do you notice? Well, look at this point right here. This is the point 6731. That means that a person had a 67% attendance and they scored a 31 on this test. As you move this way, what happens? That's 7635, right? So a person had a 76 attendance, scored a 35. Come up here. This person had a 99% attendance, scored a 49. This person had a 98% attendance, scored a 51. So we already see that the data is trending that the more you attend, so as your attendance gets bigger, your raw score is doing what?
Climbing.
It's increasing. So as x is, and we say it like this, as the explanatory variable increases, as this variable increases, x always increases, as the explanatory variable increases, the response variable is also doing what?
Increasing.
That's the first thing we do with a scatter plot. We can say that from a scatter plot by looking at it. Now, this scatter plot is nice because we can definitely see a trend. Not all scatter plots will produce something like this. As a matter of fact, the word scatter implies that the dots are going to be scattered. They can be scattered throughout. Does everybody understand that? So from some graphs, we can look at them and we'll pull the trend. From other graphs, we're gonna have to actually do some math and do some analytics with it, all right? So we're gonna start talking about analyzing the actual trend itself. And when we do that, we're going to talk about first we're gonna start off talking about what we call the covariance. So let me bring this back, share the screen. All right. Nope. So when we show our trends, from the scatter plot again, here's what can happen. Here's what happens. The X variable itself can be a positive trend. Positive means that as X increases, Y increases. Our data has a positive trend, right? And we call it the direction. The direction that it's showing right now is that as X increases, Y increases. But we could also have data that shows a negative trend. And what this says as X is getting bigger, what's happening to Y?
It's decreasing.
It's decreasing, right? Like as think about it as the number of days from payday. What happens? This is payday right here, right?
Mm-hmm.
As the days increase away from payday, what happens to your money?
Decreasing.
There you go. It's an inverse relationship. Or it's like the temperature as you climb a mountain. The height versus, so this is the height, right? As you go up, what happens to the temperature?
It decreases.
It decreases. They're inversely related. This is called an inverse relationship. That's what we call an inverse relationship. Because as one increases, the other one decreases. The other case that can happen is, well, it's very hard in this particular graph to establish a trend because the scatter is spread all out throughout. Does everybody understand that?
Mm-hmm.
Because it looks like some variables are increasing, but then it also looks like some variables are decreasing depending on how you read it. So we said, this is what we call zero correlation or zero trend, what we're gonna call it right now. We haven't called that the correlation. And it says as X increases, no relationships exist with, that should be with Y. With Y. As X increases, no relationship exists with Y. And we call it independent. I mean, the two variables are independent of each other. Things that are independent would be like, for instance, intelligence and height of adults. Intelligence and height of adults. As if to say that taller people aren't smarter than shorter people. Your height has no effect on that. Does everybody understand that? Or shoe size and the amount of money you make. Although that's kind of not true. Bigger shoe size tend to have more money. I know why. Depending on what populations you look at. Like for instance, if you look at athletes and look at how much money they make compared to the rest of the population, they tend to make more money because they have bigger feet. Not because they have bigger feet, but because, you know, they do have bigger feet. They're kind of correlated. They're correlated somewhere else though. So that's just a thought, all right? So we have those type of things, right? Now, here's what we're going to talk about. We're going to first talk about the direction and how to establish if it's a positive or negative direction. Because if we run into a case where we have something like this right here, it's going to be very hard to tell you what the actual direction is based off looking at the graph. So I'm going to develop a measure called the covariance that tells me that as if one variable increases, the other variable is either going to increase with it or decrease with it, all right? And it's based off of this formula right here, which is, I want you to understand that this is based off of, in this formula, this right here is what we call deviations. We've talked about deviations, by the way. What is a deviation? Can anybody remind me? What's a deviation?
Isn't it the distance from the mean?
That's exactly what it is. So look what I have. How many variables do I have now? It's bivariate data. So how many variables do I have? I have two variables, right?
Yeah.
One variable is X, one variable is Y. I have a mean for X called X bar. I have a mean for Y called Y bar. Do y'all see that? And I'm calculating the distance from each one of those variables. Once I calculate the distance, here's what's going to happen. I'm going to multiply those two things together like this. So whatever those deviations are, I'm going to multiply them together. And here's what should happen. If I multiply a deviation from X that is positive with a deviation from Y that is positive, you understand that?
Mm-hmm.
Multiply a deviation from X that's positive and multiply a deviation from Y that's positive. What should the product of those two things be? Positive or negative?
Positive.
Positive as well. Does everybody understand that? Which tells me that as if X is bigger than the mean, if this X is bigger than the mean, then the Y is also bigger than the mean. So that means they're increasing. likewise, another way to look at it is if I find if the x is smaller than the mean here and the y is also smaller than the mean, I'm gonna get two negatives, right? When I multiply two negatives, what do I get?
Positive.
Positive.
Which means that it's also increasing because you're moving up. That's what's happening. You're moving up. Now, if x is positive though and y is negative, what am I gonna get?
A negative.
Negative.
It's an inverse relationship. It's gonna tell me that it's inverse, an inverse relationship. And if x is negative and y is positive, then I'm still gonna get another negative, which means that these are always smaller than the y. So that's how this covariance works. So we're actually exploring the actual deviations right now. Let's go do that real quick. Let's look at that in Excel. So I'm going to bring up my data again. That's not the one I want. This one is the one I want. So we have our graph, right? And I'm going to move this graph out of my way because I don't want to see it right now. And what I'm going to do now is I'm going to make a couple columns up here. I'm going to make a deviation column, an x deviation. I'm going to make a y deviation. And then I'm going to make the product of the deviations here. And in order to find a deviation, here's what I have to know. I need to know the mean of x. I need to know the mean of y. So I'm going to calculate the mean here. And the mean is just the average. So I'm going to do the average of the x's. Is this value here, 86.36. The average of the y's is just this value here, 41.277. And then how do I find a deviation? Well, I take this x is 95 here. So I'm gonna do the first one is 95 minus the mean. And I get that value there. Make this bigger. Hopefully it makes it bigger. All right, so it made it a little bigger there. Should make the product bigger too. So this first deviation, 95, is 8 points or 8 percentage points above the mean. That's what this says, or almost 9 percentage points above the mean. The next one, how would I calculate that? Take this value
89.
and subtract that from the mean. And I get this. The next one, I would do the exact same thing. So I'm just going to drag this down. And when I do that, here's what I get. And what happened here is if I go back and explore this actual formula, by the way, it's not correct. It's not actually calculating correctly, because what it's doing is it's moving down the line, subtracting each cell behind this number right here. So it's not holding the mean steady. So to fix it, here's what I do. Because I don't want this to happen. This formula isn't right. This subtracted 67 from the cell underneath here, which is 0. That's why you got a 67 right here. This one, next one, subtract 98 from the cell underneath that one. That's why you got 98. That's why every number is just repeating itself. So to fix it, go back up here. And what you're going to do is in between the A and the 15 there, in between the A and the 15 there, you put a dollar sign. Because you want it to be static, which means you don't want it to move. You want to keep it the same. Right now it's dynamic, it's changing. You want it to be static. And so what it's going to do is it's always going to go back and subtract everything from cell A15 now. And when I do that and drag down now, I get these values.
Ah.
I messed that up because I went down too far. But I get these values there. The last one need to be there. There we go. So there you go. Here's what you get. Those are your deviations. Everybody see that?
Yes.
Now, to find the y deviations, do the exact same thing. So I'm going to do equals this minus this number there. And again, I want to drag this down. So I want to keep this constant static. So I'm going to put the dollar sign there. And I get this, drag down now. And here's what I want to, here's what I get for those. Those are the y deviations. Before we do any other math, let's talk about this real quick. Notice the deviations as pairs. This deviation is positive. This first deviation is positive for x. This first deviation for y is positive. This deviation is positive. This one is positive. Look here. When it's negative, this one is negative. When this was negative, it's negative. Did y'all see that?
Yes.
As a matter of fact, almost all of them follow the same pattern except for this one right here. That's the only one that has an inverse relationship. And what that really tells me is that something strange is happening there. And in particular, if you go to your data set and look here, the person had 91% attendance, they only scored a 41 though,
41. Yeah.
which is pretty low, right? Compared to the other values. So that's what this is saying. That person isn't following the general trend. But now we can look at their products. So to find their product, we just do this cell times this cell. Make it bigger. There goes your products. So let's do the products drag down. All you have to do is drag these down now. And there go your products. And notice most of the products. What do you notice about most of the products? They're all what?
Positive, with the exception of that one
With the
negative.
exception of this one particular value right here, right? With the
Yes.
exception of that one value, everything else is positive. So what does that tell me about my general trend? My general trend is probably increasing. It's increasing here, right? And we already saw from the graph, what is it doing?
It's increasing.
It's already increasing. I don't know
Yeah.
how to deal with that, but yeah, there it goes. It's already increasing as well. So this just confirms that it is increasing. And again, if we can look at the graph, we don't really need the covariance. But every now and then you'll get a graph where you can't really tell what's happening. And so to find the final part of the covariance, here's how we find the covariance. The formula says to find the covariance of x, you have to sum all of these products up. And you divide them by n minus 1. So if I want to find the sum of those products, so I do equals sum all these products up. I get this number right here. And there are 11 values here. So one less than 11 would be 10.
10.
So the covariance is equal to this value divided by 10. That's your covariance, 58.99, so about 59. And because that number is positive, that tells me the direction is also positive. That's what the covariance says. If the covariance is negative, that tells me the direction would be negative. If the covariance is 0, that tells me that there is zero correlation between the two, or zero direction. So you can't tell the direction, they're independent. Now, is there a quicker way to do this? Yes, we have a formula. So I made y'all do all that. I'm going to show you the formula now. The formula is just, you have a covariance formula here. And this is the covariance of a sample, by the way. So notice when I type in covariance, I get covariance P and covariance S. So y'all see that? I want to do covariance S. And it says you have to drag the array separately and put a comma. So you're going to drag down here and don't grab the actual heading, but you do the X's first, comma, and then the Y's next. And they have to be the same length or the same dimensions for this to work. If you accidentally miss a cell, it's gonna tell you an error. So we have that, we press enter, and there goes my covariance through the formula, which is the exact same thing. So this is the covariance. It tells the direction. Do we understand that? The problem with just knowing the direction is we don't know how strong or how good of a predictor this is. We just know the direction of the predictor. Right now, the predictor says that as X increases, Y is going to increase. What if we had a better measure that could tell us how strong that was? Or what if we had a better measure that gave us an idea of how good of a fit the line is? Good news is we do. So we're going to look at this next one, which is called correlation. Correlation, all right. Share content. All right. So we just talked about covariance. Covariance told us what direction we're moving in. Correlation now is this thing that's going to measure what we call linear strength. Linear strength. And the key thing there are linear strength and direction. There's two things actually. We just figured out how to find direction, by the way, through covariance. Correlation goes one step further and gives us strength. But in particular, it gives us linear strength. When I say linear strength, I want to know how straight is a line, how straight of a line it is. And in predicting things, we like using lines because lines are straight. And because they're straight, they give us an average. They give us an average, which we can calculate. And then we can develop how strong something is by finding this right here. This correlation coefficient, which we call, this is R. R is called the correlation coefficient. And it's a measure in between -1 and +1. And it's found by it's found by taking the covariance and dividing it by, what does S of X stand for? Can y'all remind me what that stands for? What does that S of X stand for?
The variance of a
Standard.
sample?
Not the variance, just the
Standard deviation.
Slope.
standard deviation. I heard
Standard
the
deviation.
So this is standard deviation of X. This other one is the standard deviation
of Y.
of Y.
It would be 2 squared x if it was looking for the variance, right?
Right. It'd be a squared X. Just a squared. S squared was what it would be. This is the covariance though. The correlation. Now, we just found the covariance by hand. I'm not gonna make you find correlation by hand. We're gonna use Excel just to give us the correlation, all right? But we could do it using this formula. But look what it's doing. It's measuring your covariance by your standard deviation. And what this tells me is this now. Standard deviation is always a positive value. You got that? So imagine the product of two positives. That's a positive on the bottom. The covariance, if the direction is positive, which way? What's going to be on the top? A positive number. So if the covariance is positive, R will be positive. You got that? If the covariance is negative, R will be negative. And if the covariance is 0, then this value will be 0. But this value is a measure of how much how much change there is with respect to the average change. That's what you're doing. So that's why the value always will be between -1 and +1. They're measures like that. The closer you are to -1. So I wrote that down here. Correlation is a measure of linear strength. The closer you are to -1, this is what I want to go to. Yeah. The closer we are to -1, the stronger the relationship. The closer you are to +1, the stronger the relationship. And what I mean by that is this. When R equals -1, this is called perfect. This is called perfect negative correlation. So when R equals -1, this is called perfect negative correlation. And when R equals +1, this is called perfect positive correlation. What that really means is that because it's perfect as one thing, in this, for instance, in this one right here, as X increases, Y will always decrease by the exact same amount. It will decrease by the exact same amount. That's why it's perfect. Here, perfect positive correlation says that as X increases, Y will always increase by the exact same amount. For example, when you go get gas, when you pump gas, right? As the number of gallons increase, can you tell me how much you're going to pay at the pump? You should be able to,
No.
right? If it's $2 per gallon and you get $10, you should pay how much money then?
Yeah, 20.
$20. You can tell me that, right?
Yes.
That's because it's called perfect positive. That's perfect positive correlation. For every gallon that you go up, what happens to the amount of the gas? It goes up by $2, right?
$2.
Now, That's because you have a set price. And we don't really use correlation. We don't really use regression for that because we know those type of things, right? But when we have variable things that change, we have a general direction of things, such as, trying to think of an example. Let's say right now, right, we're in hurricane season. Everybody got that? As the ocean or as the Gulf's temperature increases, right? What's happening to the number of hurricanes?
You're increasing too.
They're starting to increase too, right?
Yes.
Now, are they increasing at the same rate though? No, they're not.
No.
As a matter of fact, we have different data. We have a lot of data, by the way, on different temperatures and the number of hurricanes that are produced from those temperatures. Everybody got that? So when you plot that, guess what happens? You get graphs that start to look like this, where they have a general direction or a general trend, but they're not on this straight line. Do we understand that? They're not on a straight line like that. So we can start to use that trend to help us develop patterns and talk about those patterns, how strong they are. When we talk about strength, when R is less than 0, so when your correlation, this means when your correlation is negative. This first one means when it's negative. When I have negative correlation, and when R is greater than 0, this means that correlation is positive. But we know that R can't be bigger than what number? R can't be bigger than what number?
1,
1, and it can't be less than what number?
-1.
Okay, so it can't be bigger than 1 or less than -1. Everybody got that?
Mhm.
When R is in between -1 and -0.7, we call it strong negative. When R is in between 1 and positive 0.7, we call it strong. I wrote these backwards, by the way. I should write them the other way. I should write the bottoms the other way. The top ones are okay. I don't know what I was thinking. I probably just copied and pasted. It should be written like this. When R is in between 0.7 and 1. There, that's how it should be written. When R is in between 0.7 and 1, it's strong.
Okay.
All right. If R is in between -0.7 and -0.3, it's considered to be moderate. Likewise, if it's in between 0.7 and 0.3, and again, I wrote these backwards. See, they probably don't bother y'all. It bothers the hell out of me, though. That is so math wrong on so many levels. You never write the biggest number first. You never write the bigger number first in a domain like that. But anyway, so if R is from 0.3 to 0.7, like this, it's also moderate. And then the final one is if R is in between -0.3 and 0, or 0 and 0.3, we say it's weak. We say it's a weak correlation, all right? Most of the time we're looking for most of the time when we come across real things in the real world, they're normally following this moderate, if normally following this weak thing right here. Especially since we use correlation a lot for the soft sciences, like psychology. You'll see somebody come up with like a 0.2 and they'll be like, that's statistically significant, which it normally is, by the way. But most of the things in the real world happen here in the weak category because there's so many other variables that play with things. But there are things in sciences that are happening in the strong and the moderate category. But these numbers, though, I'm giving you general guidelines for them. Really and truthfully, they don't really matter. They're arbitrary. You'll see different numbers. Just know that, all right? They're arbitrary. But for us, we're going to use these numbers and go with that, all right? So if I ask you to describe the relationship, that's the thing I'm asking you to do. When I ask you to describe the relationship through correlation, I'm asking you for two things. I'm asking you for the direction. The direction can be one of three things. What are they? Positive,
And
negative,
negative.
and 0.
0.
Everybody got that? Three directions. The strength is the next thing I'm going to ask you for. Your strength can either be strong,
Strong,
moderate,
moderate,
or
and
weak.
weak.
So if we look at these different things right here, we know the directions of most of these because the directions is just a sign of R. Everybody got that? So this right here, this top two are both negative. This one will be considered to be strong. This one is considered to be moderate. The closer you are to a line, the stronger the relationship, by the way. The closer you are to a line, the stronger relationship. And the closer you are to a line, the closer it is to -1 or +1, depending on the slope of the line. If the slope of the line is negative, it's close to -1. Slope of the line is positive, it's close to +1. Here, this one is strong, this one, weak, and this is 0. 0 typically means you can draw a straight line through the data, and you can't tell if it goes up or down. All right. So let's go find the correlation for our graph. And we're going to knock out 2 things in once at this, actually. We're going to knock out 2 things at once when we do this. So here's how this works. And I used to have to download a whole data package to actually do this, but Excel's updated lately, I guess, to where Excel will do regression for you, linear regression, and it'll give you the correlation, or it won't really give you the correlation. Well, you can find the correlation. Here's the actual correlation. There's the function of a correlation as well. The correlation is CORR. This right here is the correlation function, CORREL. So use that function, and again, you do it just like you did covariance. You have to pick the X variable first, comma, and pick the Y variable next. And then close parentheses, here's your correlation. So R is equal to, this is R right here, by the way, correlation. Your R is this value. Let me make that bigger. R is equal to 0.9504. So first off, the direction of the correlation, is it positive or negative or 0? We see that the direction is what?
It's
positive.
increasing.
So that tells me, and you can look at the graph, we also got this from the graph already, as X increases, what happens to Y? It is also
It is
increasing.
increasing.
So as X increases, in this case, let's add context to that, okay? So in context, what does that mean?
It's a strong positive.
As your attendance increases, what happens to your algebra raw score?
It
Increasing.
It increases. So as the attendance increases, the raw score increases. That is how you talk about the correlation, by the way. When you talk about correlation, you say this: as the attendance increases, raw score is going to also increase. And here I can tell you that my correlation is positive. Is it strong, moderate, or weak?
Strong.
It's strong.
It's strong.
It's
And even if
strong.
I looked at this graph, I could tell you that it was strong too, because look how close to a line it is. This data is very tight together, so it's very close to a line. So this is what we call a strong positive relationship. It's a strong positive relationship. And by strong positive relationship, it's actually a strong positive linear relationship. That's the value of R. So that's how you find R using the actual Excel. Now, we could, if we wanted to, find R this way too. The formula for R is the covariance divided by the product of the standard deviations. So this is a sample again. The standard deviation of this one is this. You have to use parentheses to make sure this works out right. Times standard deviation of this is this. Messed that up some kind of way, but anyway, there it goes right there again. That's through the actual formula. So all I did was I took the covariance and divided it by the standard deviation of my x's. Let me write that formula. Let me write that down. S of x is equal to SD standard deviation S, by the way, because we're taking samples. That's standard deviation of x. SY, standard deviation of y, is equal to this. Drag that down. That's standard deviation of y. To find the covariance, to find the correlation, we do the covariance divided by the product of those two standard deviations. So you multiply them together. This times this. That's your correlation, which you have right here too by the function, by the formula. So the correlation is given to us there too. And we see our correlation is strong and positive. And we understand that the correlation means that as the X variable increases, what happens to the Y variable?
Increases.
Increases also.
So
Increases.
that's all the correlation tells us, all right? So now that we know how these things are working together, how they're trending together, we want to make predictions. And we want to make predictions, we use what's called linear regression to make predictions. So the last part of this entire thing is what we call linear regression. And so in linear regression, let me bring that up. We talk about linear regression, here's what we have. You may know linear regression as the line of best fit. So most people who've taken algebra class or taken any kind of math class, they'd be given a scatter plot like this, they would tell you to pick 2 points and then write the equation of the line between the 2 points. Or you get a set of points like this, you try to draw a line through all the points. Try to draw a line through as many points as possible. So linear regression is basically the line of best fit between 2 quantitative variables. We call it the least squares regression line. So linear regression itself is the process of predicting. This is just the, linear regression itself is the, this is the method of predicting using a line, hence the term linear. It's the method of predicting, I probably can't see that, I can barely see that. The method of predicting using a line there, right? And that line is called the least squares regression line. And here's why it's called that. It's basically a mean for the data. It's a mean for bivariate data. And what it does is that line is going to minimize, it's going to minimize our deviations away from it. It wants to minimize the deviations. But remember when we talked about means, when we talked about standard deviation, what happens when you find the deviations away from the mean and you try to add them all up and find the average? We always got what number? What number do we get? Remember we tried to add up those deviations to find the standard deviation?
0.
We got a 0 value, right? How do we fix it?
Square.
We squared. Here's why it's called the least squares regression line. It does the exact same thing, except what it's trying to do is minimize these vertical deviations away from the line. It wants to minimize those, and it minimizes those by making squares out of them, by the way. But the line itself is an average. And on this line will always be the point X bar, Y bar. That is always on the line, the average point. So on our line that we're doing right now, we would always have the points, which were 86 and 41, I think. 86 point something and 41 point something. That point is going to be on our line. And it's used for predicting unknown values based on, here's the key thing. We make predictions based on known values. We make predictions based on known values. And when you make predictions based on known values, you're doing what's called a safe process known as interpolation. This is called interpolation. Interpolation. It means you're interpreting from what you know, from a known range of values. And we predict based on the X values. So in our particular case, when we interpolate, we're interpolating based on these values here, knowing what these values are. And in particular, you line these values up, the X values from smallest to largest. The smallest value we saw was 67. Here's the smallest value of 67, and the largest value was at 99. That means that anything within the range of 67 to 99, we can be pretty sure about because we have data covering that. We know what's happening inside of that range. Anything outside of 67 to 99, though, we are unsure about. And there have been many a times when people have tried to make predictions based on things outside of a range. When you make the prediction based on something outside of the range, that is called extrapolation. Interpolation is safe. Extrapolation is dangerous. This is dangerous. And what happens is if we don't know something about the information outside of a range, we're really guessing. We don't know what the graph, like for instance, we don't know what our graph is doing past 67. Because we're assuming that it's on a straight line right now. We can see that it's on a straight line from 67 to 99. But outside of 67, it could be curving somewhere else. All right, so that could be happening. And a famous example of extrapolation, the Space Shuttle Challenger, you know what happened to Challenger? Back in the 70s, what happened to Challenger? It blew up.
Loaded.
Yeah, and do you know why it blew up? Well, it blew up because the O-rings didn't seal correctly, didn't seal properly. And they didn't seal properly because NASA had all this information on different temperatures at which to launch at. And because of pressure, financial pressure, and they had scrapped the launch a bunch of times before. They were supposed to launch sometime in, I want to say in August. It got moved to November. Then it got moved to February. So it went from having high temperatures around 80s to the 80s, 90s to having a high on that day of 55 degrees. At that particular time, NASA had never launched a space shuttle under, I think it was 70 degrees. They assumed everything would be okay though, extrapolating from the data they already had. What they didn't take into account is that machine failure occurred at a certain temperature. In this case, the O-rings did not seal at such a low rate. So what ended up happening was the oxygen backed up into the fumes backed up into the space shuttle and it blew up, all because they extrapolated the data. All right. So extrapolation is a very dangerous thing to do. And extrapolating means you take data, you try to predict something based off what you don't know. And so the purpose of regression is to actually predict on what you do know. I want you to understand that. We're predicting what we do know. That's called interpolation. So when we talk about regression, here's the actual regression equation. This variable right here is called y hat. It has a hat above it. This is called y hat. Y hat is the hat. When you see a hat above something, a hat means it is a prediction. It is a prediction or it's an estimate of something. That's called y hat. This equation should look very familiar to you if you've taken an algebra class, because it is basically the equation of a line, where a line is y equals mx plus b.
Mm-hmm.
Y'all see that? Y equals mx plus b.
Mm-hmm.
And let me rewrite that equation, by the way. I'm going to rewrite it to what looks like the linear regression equation. Line is y equals mx plus b, so I'm just going to write it as y is equal to b plus mx. That's the same thing. Right? Where in our equation, b stands for the y-intercept, m is the slope, and then x and y are the independents. All right, independent is x, the dependent is y. Here we have y hat equals, this is called beta naught or b0 or whatever. It's the y-intercept. It's your starting point of the function. It's the starting point of the equation. It's when x equals 0, here's what you're going to be at. This right here is called the slope. b1 is the slope. b1 is the slope. All right. Now, technically, I'm supposed to give y'all more information about this. As a matter of fact, what you should know is that there's also what we call this, let me call it Greek. There's also this error term E that sits out here. There's an error term E that sits out here. And the error is the part of the equation that allows you to predict, actually. It allows you to predict. Because this is a straight line right now. You understand that? And we know our data isn't a straight line. So this error term allows us to predict. Because we're predicting, what ends up actually happening is this error term is really just 0. So we don't really worry about it. The error term is really just 0. So this is the equation we get, and we're going to predict with it And we're going to interpret the actual variables that we get from it. In particular, the one I'm really concerned about is the slope. The one I really want you to understand an interpretation of is the slope. And so when we talk about our slope, V1 itself, the slope, here's how you interpret it. And this is a blanket interpretation that you can always use. For every 1 unit increase in the X, there is a slope increase or decrease, depending on what the sign of the slope is. The slope can be positive, it's an increase. The slope can be negative, it's a decrease. But whatever that is, you're going to increase or decrease in the Y by that amount. And that's how we interpret the slope. And what the slope is basically saying, this is an average increase or decrease that you're doing. So on average, for every 1 unit increase in the X, there is a increase, a beta or B1 increase or decrease in the Y. And we know that our variables right now are, the ones we're going to deal with in a second are going to be, for your X, what's the X variable? That's attendance. And we know that the Y variable is the raw score, right? So when we start talking, we'll say for every one, we know the unit for attendance was percentages, by the way. The unit for attendance is percentage. So for every 1% increase in attendance, there will be when we find the slope. By the way, is the slope of the line going to be positive or negative? Do we know that from the graph? Yes or no?
Yes.
Yeah, we know the slope is going to be what?
Positive.
Because R, and that's another thing that's nice about the slope. The slope and the correlation have the same sign. Slope and correlations have the same sign. Do you understand that? Slope and correlations, you have the same sign. So if your slope is positive, your R should be positive, and your slope should, and your beta, and your B should be positive. I'm sorry, B1 should be positive. So if your slope is positive, then your R should be positive. If your R is negative, that tells me my slope is also going to be negative. All right. They have the exact same signs. But here's what we're going to say. For every 1% increase in the attendance, there is a beta 1, it'll be an increase. We need to figure out what B1 is. B1 increase in the raw score. That's how you interpret the slope. So in order to do that, we have to actually do regression. So to do regression is very simple using Excel. And in Excel, to do regression, I'm gonna go back to Excel real quick, share screen. They've updated Excel very nicely to where now you can do Excel, you can do regression right on after you do the scatter plot or right after you do the graph. So all you need is this graph right here. All you need is this graph. Or all you need is the actual scatter plot like this. And what you're going to do is, for the graph, if you click on it and I go to chart design, you go to quick layout. If you go to quick layout, you can change the different designs of this particular scatter plot. For instance, you can add this line right here, which is the trend line, which is basically the regression line that you're adding. You can also add, even better, you can also add that trend line. You see where it says f of x at? This is the linear regression equation that it's adding. And I'll blow that up for you. It gives you two things, by the way.
Okay.
Better not make it bigger. There. It gives you, first off, it gives you the equation, which in this case, the equation is y is equal to 0.5669x minus 7.688. Your slope here is this first term right here. Here's your slope. Don't do that. Your slope is that part right there. I was just trying to highlight that. There. That's the slope.
Which layout did you use?
I used the one that had f of x on it. Do you see it? Chart design. Quick layouts. You see it right here? This one, layout 9.
Okay, 9.
Do y'all have that one?
Mm,
I have that one. I hope y'all have it too. It makes it so much easier.
You'll teach. You'll teach.
Somebody else got a question? All right. So this is the slope at 0.5669x. Here is the y-intercept, this negative 7.688. What does that negative 7.688 mean, by the way?
There should be a decrease.
Think about that real quick. Think about what that negative 0.7688 means.
It's the prediction of where when it touches the y-axis, that's where it's
So,
gonna land.
in terms of this problem, that's what it means. It's actually the y-intercept. So where across the y-axis at? That means your x value is going to be 0. Your x value is going to be 0, right? And x stands for what? Attendance, right? So if a person never attended class, if a person never attended class, what does this say then? They're predicted to make a
7.6888.
no. They're predicted to make a negative 7.6.
Negative 7.
Negative
So what does
76.88.
that tell you about attendance in general already? That it has a
220.
positive effect on your score. You
Yes.
understand that? Because without doing it, what's going to happen? You're going to have a negative value. So if you actually attend, then you should have a positive value on your score. As a matter of fact, if you don't attend at all, you expect to score negative 7.688. Well, can you do that? No. You can't do that. You can't score negative 7.688. You can probably only score a 0. You just score a 0 is what they're saying. But that's what kind of effect it has on you. So the y-intercept tells you what happens if x is 0 or where you start at. That's where you start at. When x is 0, in this case, when our percent attendance is 0, we're going to score a negative 7.688 on this test. And then if I want to interpret the slope says this. For every, remember, this axis right here is the, I'm trying to change that axis title.
Just type it inside.
There you go. So this is percent attendance, right? Bigger. So for every 1% increase, 1% increase in attendance. I don't know what those lines are, but for every 1% increase in attendance, the Y is the raw score. Drop that down, son. For every 1% increase in the attendance, there is a 0.5669 increase in your raw score. For every 1% increase in attendance, there is a 0.5669 increase in the raw score. That's how you say that. Does everybody understand that? Slope is one of the most important interpretations in all of statistics, because it is an on average interpretation, actually. And actually, we should add the words on average when we say that. On average, for every 1% increase in attendance, there is a 0.5669 increase in raw score. That's the first thing we're going to say. That's what we say there, all right? Now that we know the equation, and also notice this, when I did that formula, by the way, I got this value called R squared. We found correlation by using the actual correlation formula. This formula can also give me R, the correlation. If I take the square root of that number, 0.9034, if I take that number, the square root of that number, I get that 0.95047. So this chart, this actual formula, the chart design itself, actually gives you the correlation, by the way. You just need to take the square root of R squared. R squared is called the coefficient of determination. We're not going to worry about a whole lot what it means right now, but it's called the coefficient of determination. And what it really just tells you is that based on these two variables, 90% of the variation between attendance and score is explained. So the other 10% of your score depends on something else that we're not looking at. But 90% of your score right now can be explained by your attendance. The other 10% may be explained by how intelligent you are, what kind of class you're taking, how big your foot is, what's your mama last name. We don't know. But that's what this is saying right now, right? It's called the coefficient of determination. We're not going to worry about that. What we are going to do now, though, is this. Now that we know that actual equation, I want to make predictions with it. I want to make predictions. And here's how I want to predict. I want to predict inside the range. I want to predict inside the range. So I want to look at a number like, let's figure out if a person has an attendance. If a person has an attendance of 80. If their attendance is 80%, do we have a value for 80 inside our data set?
Yes, you got 82,
We don't have 80 though. We
Not
have a number
really.
around
80,
82.
80.
We
No.
don't have 80. We got an 82, which is 8 should score 37, right?
Mm-hmm.
Looks like the next value close would be 85, or we have a 70 something.
76.
76.
76, they should score 35, 38. So let's see. If we take the value of 80, so with an attendance of 80, the predicted value, the predicted score, plugging into that formula is equal. So we're going to take 0.5669 times 80 minus 7.6888. So all I'm doing, I'm plugging in the formula. And what did I do? I replaced the X with what number?
80.
80.
All I did. When I do that, look at the score, I get a what?
37.
37.663.
37.
Does that answer make sense?
No.
Not really. I mean, kind of.
The
Kinda.
answer itself, we need to do what to it? Either round it up or down, right? Make it a whole number.
Yes.
So about 38. But does that answer make sense based on our data? Yeah,
Yeah.
because look at here, you have an 82,
82 is
what?
at 37.
37.
37.
It's pretty close to that. 76 was at
38. 35
right?
and 38. You got two 76s.
Yeah, 76, you got a 38 there. So that's pretty close. That generally agrees with our data. Let's pick a number like 85. Do we have an 85 in our data set?
Yes.
Yes. And this time we're actually going to compare the two values. So for 85, again, plug into the formula, y is equal 0.5669 times 85 minus 7.688. I get 40.9, I get 40.5, right? Does that agree with my data over here? Does that agree with this 85?
Yeah.
They're fairly
Yeah.
close, right?
Yeah,
They're
Pretty
very close.
As a matter of fact, how far off is this particular value? How far off is the value? We can find that when you know the actual value. We know our actual value here is 39, right?
39.
Yeah, our actual value is 39. If I know the actual value, I can find this thing called a residual. A residual. A residual is basically the vertical distance from the predicted value. It's the vertical distance from it's the predicted value, vertical distance from the predicted and actual values. So what that means is to find the residual is always equal to the actual value. The actual value minus the predicted value. So the residual is always equal to the actual minus the predicted. We know our actual value is what? Our actual value is 39.
39.
Our predicted value was 40 point,
40.
so we'll call it 40.9. We'll leave it like it is.
40.5.
We'll leave it like it is, 40.4997. We can call it 40.5.
Okay.
There's our residual. Negative 1.5 about, right?
Mm-hmm.
So our residual is negative 1.5. And now here's what this tells me then. I want to know, here's the question I really want to ask. Did this line overestimate or underestimate the actual value? We can see from the data the line did what? The actual value was what?
39.
right? The predicted value was what?
40.5.
40.5. So did the line underestimate or overestimate?
Overestimate.
Overestimate.
And here's what I'm going to give you.
Overestimate.
On your test, here's what I'm going to ask you. I'm going to give you a set of residuals. If all of the residuals are negative, what does that mean? The line did what?
Overestimated.
It's overestimated the entire time.
Overestimated.
If the residuals are all negative, that means the line is overestimating the values. Everybody got that?
Mhm.
It's opposite of what you would think. If they're negative, it's overestimating. And if they're positive, what does that tell you? The line is underestimating. And that's because you're measuring the distance of the actual from the predicted. If they're positive, that means the line is all the way, the line is always underneath them. And if they're negative, that means the line is always over them.
Over.
So we call residuals, all right? And so the residual is just the deviation that you have from the actual line. How far the point is falling from the predicted values are falling from the actual value. But you guys, that is pretty much all linear regression is. There's more that we could do. We're not. But the last thing I need to tell you is residuals, and that is pretty much everything we need to know right there. So we know how to find the correlation. We know how to find the regression equation. We know how to predict with the regression equation. We know how to find the residual from a prediction. That is what linear regression is. And again, you can find all of that stuff. Honestly, we did everything. I showed you how to find everything, right? You could have literally just highlighted this right here. All this stuff. Went to insert chart, recommended chart, clicked on the scatter plot, changed the chart design, quick layout, changed the chart design to this, and you would have got all your information, by the way. Right here, you got all that information there. So we did it the long way, but the quick way, and the way you would do it on your homework, because they may actually define regression equations on Blackboard, on My Math Lab. If they actually define regression equations on My Math Lab, copy and paste the stuff into Excel, and just do the quick chart, the quick layout chart, all right? And then it'll give you everything you know. It'll give you R squared. I showed you how to get R from R squared. Take the square root of R squared. That'll give you R. Remember that when you look at this, R squared itself will always be a positive value, by the way. Here's another thing I can do. If I tell you that R squared is this value right here, and I ask you for the value of R. So if I tell you that R squared is 0.9034, can you give me the value of R? The answer there is no, you can't. Because R is a value that has a direction. It can be positive or negative. R squared will always be positive. So the only way you can give me the value of R is if I give you the graph of the data, which shows the direction is negative or positive, or if I give you the regression equation. Here, because I'm giving you the regression equation, right? Here, because I've given you get rid of this graph. Here, because I'm giving you the regression equation, you can tell me that R is going to be what?
The square is going to be.
I know R squared is it, but to get R, I take the square root. When I take that square root, it can either be positive or negative. It has to be what this time, though?
Positive.
Positive.
Because the slope of the line is what? Positive.
Positive.
If the slope of the line is positive, R has to be positive. If the slope of the line is negative, R has to be negative. So if I don't give you the equation or if I don't give you the graph, you can't tell me what R is. You can give me the value of R, but you can't really tell me if it's positive or negative. That's just something to keep in mind. I don't think I'm going to do that. I may give you regression output, though, and ask you what's the value of the correlation. So you need to make sure you be careful with that. I may give you something like this and ask you, what is the value of the correlation? I'm telling you, I will do this, by the way. I will do that. I will give you a graph. I will give you an equation just like this with no graph. And I'm going to say, what is the value of the correlation? And one of the answer choices will be 0.9034. One of the answer choices will be 0.5669. One of the answer choices will be negative 0.7688. One of the answer choices will be this right here. The other answer choice will be a negative version of that. You need to pick the right answer. You should be able to do that, though. But anyway, do y'all have any questions?
So you said we should be able to find it by just doing the square root of it and then looking at the
Slope.
graph or the slope to determine if it's going to be positive or negative. But the
Right.
square root is always going to be the answer. Just the direction is what we need to figure out,
That's
correct?
what you have to figure out for R, yeah, because R has a direction. And you can't tell the direction based off of R squared because R squared is a positive value always. So you have to look at either the graph or you look at the equation. If you have the graph, it's easy to tell the direction. If you don't have the graph, the equation gives it to you. The direction is given by the slope. All right. I think that is it. I will try to get a review put up by Thursday. I'll try to get a review put up by Thursday to help you out with this. We may or may not have class on Thursday. We may have a review party on Thursday. I don't know. I haven't decided yet.
I'm all for a review.
I might
Review.
I'm perfectly okay with having a review day. It's up to you though.
Yeah, I know. Anyway, somebody asked in the chat about notes. Yeah, you can. I think I'll let you use your notes on it. I mean, I'm not gonna be there to police you. I'm not making you do it through monitor, so I won't know if you use them or not. To be honest, it'll be more of a honor system thing. And y'all seem like a bunch of honest people, by the way.
Thank you. We are.
That was sarcasm.
I know.
Anyway, all
Back
right.
at you.
So
I would say you should consider what I was telling you earlier about just, making your life easier. But
all right. So Thursday, we may meet for a little while. We may meet for about 30 minutes on Thursday and talk about the test. And I'll try to get a review by Thursday, all right?
Thank you.
All right.
Thank you.
Yes, sir.
Y'all have a good night.
Nice.
Y'all have any questions? I can go. Y'all have a good night.
Thank you.
Mhm.
Good night.
Hey, you people that are still hanging around, I got questions? You got the people that are hanging around, y'all still got questions? Y'all got questions? Rue, Cynthia, questions? All right, y'all have a good night.